In this lecture, we want to continue our discussion of generic programming and take a look at parameterized types. Parameterized types provide a way to specify the exact type of object you want to store in a container. The reason we want to do this is so that we will get compile time rather than runtime errors. Parameterized types were introduced in Java 1.5. And that was the goal, to produce compile time rather than runtime errors. This provides better type safety. Type parameters let the application programmer specify the kind of object to be stored in the container. If you try to insert any other kind of object, then you'll get a compile error. Passing the wrong kind of object into the method for one of these container classes will also generate a compile time error. The actual underlying type in the container is still the object superclass. However, we use the parameterized types to represent any kind of object. Type parameters are enclosed in angle brackets, and by convention they are a single capital letter. So in the application program then, you place the actual type you want to use in angle brackets, and that follows the name of the class. So rather than class stack, we have class stack person equals new person and then the size. So the benefit to doing this is that we can only insert or push instances of class person onto the stack. If we attempt to push, say, a double 1.0 onto the stack, the code will not compile. This leads again to compile rather than runtime errors. In the data structure, this is the data structure that the application program is going to use. We write the parameterized types as the single letter, generally E or T, in angle brackets after the name of the class. There's a listing here from the Java documentation about what is recommended for the letters. In general, if the data structure takes a single parameterized type, then it's an E or a T. If it takes two parameterized types, for instance maps or dictionaries, for that you would use K for key and V for value. Here's an example of class stack written using parameterized types. So we have public class stack E. Then the data for our stack is going to be stored in an array. We have given this the name storage. Notice the declaration here. We have E square brackets to designate that it's an array, and then storage. Now it turns out that we cannot create a generic array. So we will need to actually do something to make this work. So we'll see in the constructor here we have storage equals, and then an array of type E in parentheses. This is a cast, new object max size. So on the left hand side we have an array of type E. On the right hand side we have an array of type object. Notice too that in the constructor you don't place the E in angle brackets. The general rule is anytime you have the name of the class, i.e. stack capital S, then immediately following the name of the class is the E in angle brackets. Then where you would normally have object, for instance the next method, the pop method, the non-parameterized type version we have public object pop. The object now becomes an E. So every instance of object changes to E. In the push method, in the generic version that did not use parameterized types, we had public void push object obj. But here with parameterized types, we use E. Some notes here. The generic type parameter, which is usually an E or a T, goes in the data structure class. It does not go in the application program. The actual type goes in the application program that uses it. So where you're actually creating the stack and using the stack, you put the application type. The general rule is this: if you know what the type is, then you specify it. When we're writing our stack class or our linked list class, we don't know for sure what it's going to hold, so we use ease. However, in our application, when we create and use a linked list, when we create and use a stack, we know what kind of object we want to put into the linked list or the stack, and there we specify it. So in the data structure, the parameterized type follows the name of the class, and when the object would appear, you use the parameterized type instead. When you compile your class, you have a single class file that doesn't have any actual type in it. This is called type erasure. This differs from other languages such as C++. The C++ language has a construct that looks very much like these parameterized types. In C++, they're called templates. But there's a major difference here. With C++ templates, when you specify a type in the angle brackets, you will get object code with that exact type in it. So if you have to use, for instance, 5 different stacks, you need stacks to hold 5 different types of objects. With C++, you would get 5 different sets of object code, one for each specific instance of the type required. However, with Java that doesn't happen. You have a single class file, and it is not recompiled for every project when you use it. There are consequences of this. First, you cannot instantiate a generic type. We cannot say eTemp equals new E. We can't do this because we cannot be certain that a constructor will be found that matches. There are some classes that don't have empty constructors, and so you cannot be certain that there will be a match, therefore this is not allowed. The other thing you cannot do is you cannot create an array of generic types. Arrays are by their nature not type safe because there's an extra level of dereference. So we cannot ever say E square bracket storage equals new E max size. That is, we cannot have an array of type E on the right-hand side of an assignment. We can have an array of type E on the left-hand side of the assignment statement as long as there is an object on the right-hand side. So in the example here, the next 2 lines we have object square bracket storage equal new object max size. This is okay. And then we have E square bracket storage equals cast2 array of type E new object max size. The second form is better because it avoids excessive casting. Also, you need to be aware that you're going to get class cast warnings with generic code because the compiler is unable to guarantee that the types are compatible. Some additional details. There is a diamond feature which was introduced in Java 7. It's designed to make coding easier. However, it only works with Java 7 and later, and so if you try it with Java 6, you'll get compile errors. In this case, stack string stack equals new stack, and then we have the empty angle brackets here. That's called the diamond. And this can be done because the compiler can infer from the declaration that string goes in there, and so there's no reason to put it twice. In certain collections, certain data structures, you'll have more than one parameterized types, and you can have multiple parameterized types. So here's an example, a hash table that takes a key and a value pair. Typically, we will use the capital letters K and V for this. Later in the semester, we will study a type of data structure that holds keys and values. These are dictionaries or maps, and the idea is you have a key that's used to look up a value, a telephone number that's used to look up the customer's name, a red ID that's used to look up a student record. We also have the wildcard, which is the question mark in angle brackets, and that can represent any type. Use this with caution. It can undermine type safety. Parameterized types cannot be primitives. That is, remember there are 8 primitives, such as int, float, long, short, byte. Each of these have object versions that match. So the object version of int is integer capital I. So you must always use the object version for the parameterized types. Now when you're actually using the code, you can insert, for instance, primitive types. So in the code given here, we're inserting the int2 into the linked list, and the casting happens automatically. This is called autoboxing. So you do not have to say list.insert first, new integer 2 in parentheses. You need not do that. It happens behind the scenes. Also, parameterized types support bounds. What this allows you to do is to use a range of or a set of classes as your parameterized type. Use these with caution. So there are 2 ways to do this. There are upper bounds and lower bounds. Here we have question mark extends number. So this is the number class or any of its descendants. So if you look at the inheritance hierarchy for class number, you will see that it is all of the number types: byte, double, float, integer, long, short. The lower bound, question mark super integer. This is the integer class or any of its ancestors. And there are 2 ancestors of the integer class, object and number. Again, use these with caution because you're relaxing the type safety guaranteed by parameterized types. Class cast warnings are inevitable. You will see them. You can use the -excellent switch to review all warnings. And the X here should have been capitalized, and it's not. As you can see in the code I've copied and pasted, I have tried to compile linklist ds.java, and I got an unchecked cast warning. These warnings occur because the compiler cannot verify the type, and that's because of type erasure. So here we have a cast to comparable E for current.data. However, the compiler cannot be certain that current.data, the object stored in that class, actually implements the comparable interface. Therefore, you're going to get these warnings. You want to look at them and make sure that these warnings are for things you can't do anything about. Very often in student code there are a lot of warnings about unchecked casts, and these will come because the students neglect to put the parameterized types. And so where you have comparable E, you should put comparable E. Once you're satisfied that you have eliminated as many of these warnings as possible, then you can put the @suppress warnings tag, and then when you compile the code, you won't get any more warnings from it. You're going to get these where you use the comparable class and where you use arrays. So examples here, we've got a main method, and we want to create a linked list and use it. So this is the application program, and we have list ADT integer, list equals new array list integer. That is the type. Here is the array list, the data structure. And it takes type E, not type integer. Integer goes in the application, but the data structure itself uses the parameterized type. We want to be able to put any type of object inside our array list, therefore we use the E. So notice we have an array here of type E, and when we create it, we cast to an array of type E, but we're actually creating an object array. Then we have the contains method, and so in the contains method it takes the parameter E obj, and notice that we have comparable E obj.compareTo, and then the array element list I. Remember that what makes this work is polymorphism. That is to say, we cast our OBJ parameter to comparable, which means at runtime, the compare-to method in this particular object, whatever it might be, is found and used. So the JVM will find the appropriate compare-to method at runtime and use it to do the comparison. So in generic code, we're coding the pattern. We have this comparable or compare-to method pattern that we use, and then at runtime the actual code is found and used. And this allows it to be generic. So this concludes our discussion of generic types and type parameters.